back to our design of mechanical components. So last time we reviewed a little bit of mechanics of materials. This time we are moving forward. So I was really quick on this particular slide last time. I want you to make sure when you go back, you are able to calculate the area moment of inertia. Okay? So if you don't remember about how this balance of moment was completed, so we can derive an equation like this. If you don't remember it, that's okay. Because the important equation you need in this course is this one. Okay, so last time we started with balance of moment. This is the moment you provided to the system. And this is the moment the other half of material applied to this particular system. So these two moments balance out. This goes to the left-hand side of the equation. The rest, the integral, the sum of all the moment everywhere on the edge can be computed by this integral. The integral basically is a summation, adding up everywhere. So if you focus on this area, if we focus on this particular point, when you view this from the side, basically from the side we have a rectangular area right here. That's dA. Okay? So this is a little bit higher than the location we observe. So the y represents where we are observing. Okay, so this is a small area, and we want to compute the force applied on that pink area. If you use stress multiply area, you have force. So this stress multiply area, that's force. This is the force pulling toward right, multiplying the distance, then you have a moment clockwise, right? So multiplying the distance, this is the moment going clockwise. And the moment you apply goes counterclockwise. That's why they balance out. And over here we assume the stress is linearly proportional to the position. So when we are at a neutral position, there's no force. When we move up by y, we assume the stress is k times y. We don't know what is k yet, but it's a constant. It's a linear, it's a slope. So since it's a constant, it could be taken out of the integral. After you rearrange everything, you have that. So you can actually get k equals to m over what's left. And this is exactly the calculation of area moment of inertia. Okay? So if you, because k equals to sigma over y, then you can have sigma on your left-hand side, you can move your y to the right-hand side, and you can replace this complex calculation by I, the area of moment of inertia, then you have something like this. Okay, this equation works for other geometries. So all you need to do in the future is to check some internet or your textbook. You can find, okay, what is the equation for area moment of inertia when you are working on different kinds of shapes. So over here, when you check your textbook, usually you see this. and you see Ix and Iy, what's the difference? So the index is representing one axis, either the horizontal one or the vertical one. If it's representing the horizontal one, that means you are like bending about that axis. Okay? So in our case, when we are viewing from here, from the side, we are like bending this way, right? So when we view from here, we are bending about this axis. In our coordinate, this axis is actually z. But the textbook will not match whatever axis you are working on. You just need to transfer by yourself. So it's like you are viewing this way. If you name the horizontal distance right here as b, name the vertical as h, the total height. Okay, so that matches the index, the symbol that we're using in the textbook. But the only difference from the textbook is that in our example, the horizontal axis is called z, and the vertical axis is called y. So to be accurate, in this particular case, you can only say this I is IZ, because we are bending about the horizontal axis. Okay? But when you are trying to match the coordinate in the textbook, it's actually this one. So you use the equation of Ix. So this x is representing which direction that you are bending about. Okay. So I use BH cube over 12 in this particular case. Okay, BH cube over 12. Okay. So you have learned this already, actually, but if you didn't learn. If you already forget about this, or you didn't learn well in the previous course, you must understand this in this course. And this is the equation that we use almost the entire course, because we are always dealing with bending or twisting, and we are always dealing with something long, like a cylindrical shape or like a rod. Okay? So please make sure you know about this. Now, what is the maximum stress? Can someone tell me? What is the maximum stress in this case? Y equals to what? Y equals to, someone tell me? When y equals to what, we have maximum stress? No, C. Yeah, or half of h. Yes, you're right. Okay, so the maximum stress equals to mc over I. Okay, make sure you know how to do it. Now, that was normal stress. Now we talk about shear stress. So basically, we could be twisting a cylindrical object like this, and we are doing the same trick. However, this I feel like sometimes it's harder for students to visualize. So please bear with me and see if you can understand this time, if you didn't understand well in the previous time. So now you generate a torque going clockwise in the back and going counterclockwise in the front. So you are twisting it. And originally, before the twisting, there is a dashed line right here. And we exaggerate how the material was twisted. After you apply the torque, this dashed line was twisted to this new dashed line right here. If you have good imagination of a 3D object, you probably think, okay, this is not a straight line. It should be something like a curve. You're right. But we are exaggerating very small deformation. So think about this as a metal cylinder. If I try so hard to twist a metal cylinder, it will deform slightly. I can barely see its deformation. So we are actually talking about that kind of small deformation. But this figure exaggerates how much the material is being twisted. Okay, so which means this gamma is so small, you can barely see it. When we have so tiny deformation like that, this dashed line, you can say is a straight line, still a straight line, okay? So when you twist this dashed line to here, the angle right here is gamma, and the angle right here is theta. Okay, later on we will use those geometrical information to derive some equations. Now, same trick. If we make a cut of the material in half, then in this case, I think we are talking about, it's like we cut in half and we are working with the piece in the front. So there is a counterclockwise torque going this way, so that's this guy. And the other side of the material is fighting against of your twisting. It's twisting toward the opposite direction. So the material from the back is fighting against this twisting. So it's going clockwise. So whatever I'm drawing right here is the other half of the material is trying to making some kind of twist inside the material. So we also assume that the stress being generated at this cut is a linear model as well. So why? Because at the neutral axis, if you after the twist, you don't see any deformation in the center. If there's no deformation, then we can assume there's no force right there, and also no stress. So then since we assume it's a linear model, we focus on particular position with a radius r right here, and the stress on the surface is going this way, is named as tau, because it's a stress applied on the surface. It's a shear stress. It's a normal stress. So it's going toward right because it's gonna generate clockwise a moment to fight against the torque that you generate from outside. Okay, so same trick. We're going to compute the torque that's generated by this level, and then we're going to sum them up. But when we have the amount of stress, we are going to compute with the area. So pressure times area, that's force. Stress times area, that's force. So when we are working on the area, we not only focus on this point, we focus on the entire ring. The reason why is because all the forces that is applied inside the entire cylinder is exactly the same. It's you can say it's a axial symmetrical. So it's everywhere is the same. So whatever you compute right here is exactly the same right here everywhere, as long as the radius is the same. So why don't we compute the entire ring at the same time? So we have the same amount of stress going toward the tangent direction around the ring, and the entire ring area is the stress area. So we call this stress area as dA, the entire ring as dA, multiplying the exactly same amount of stress applied everywhere. When we multiplying both of them, we have the total tension force that's going around this ring area. So that's force. And if you have force times radius, then you have moment. So basically same trick. It's just, the only difference is that the geometry is different from previous page. So this is stress times area, this is force surrounding this ring, multiplying radius, that's the moment surrounding this level. So this only gives you the moment that's contributed by, on top of this ring, contributed by the force applying on this ring. So we need to sum them up. We need to sum everywhere. That's why we use integral. And whatever is changing is r, the position that you are observing. So you start summing up, starting from r equals to 0 up to r equals to capital R. Okay, so this r represents the radius of the cylinder, and this capital R, capitalized R. Okay, so overall, that's the total, you can say torque generated at the cross section, fighting against the torque that you generated from outside. Okay, so they balance out, and over here, since we have a linear model, tau equals to kr, we apply back to the equation. You have something similar right here. K is a constant, you can take it out. At the end, you have a very similar equation right here. However, now it's a r squared. Okay, so we are now working with a polar coordinate. It's a different way to compute the area moment of inertia. So we call this guy as J instead of I. It's a polar area moment of inertia. And you can also check your textbook to compute it. And if your book only gives you Ix and Iy, J equals to, sometimes they call Iz. This equals to Ix plus Iy. Okay, so you can write it down somewhere in your notes. So in the future, if the book doesn't give you J or Ix, then it's the sum of Ix and Iy. Okay. So at the end, Kr goes back to here. So I have tau over r. So r goes to the right hand side. So I have tau equals to t r over j. Okay, j you can find it from the textbook. So comparing to the linear stress analysis for the shearing linear analysis, tau equals to g times gamma. Tau is your shear stress, and then gamma is your shear strain. Okay, so shear strain basically is the angle, how much you twist right here. Okay, and g basically is the shear modulus. It's representing how strong a material can be twisted to fight against its twisting. If it's a larger g, then you can hardly twist it. If it's a smaller g, you can twist it easily, more easily. Okay, so from geometry, usually when we observe twisting, we usually don't measure this angle. We usually measure this angle. We usually describe the angular deformation to represent how much twist we have. So sometimes we are interested in how large this theta is. So over here is for the calculation of theta. So what is r theta and L gamma? Basically is this arc length. Okay? r theta is this arc length, that's no issue. But L times gamma equals to this guy is a little weird, because you don't see, it doesn't look like a circular arc along this way. However, as I mentioned, we are dealing with very small deformation. So when this gamma is so small, the arc length right here is almost the same as L times gamma. So this equation is only valid when we are having very small deformation. Okay? So this arc length can be computed by radius times theta, also radius times theta right here. Only valid when we are having small deformation. When we have this, then we can put everything together. Then we end up with this angular deformation, how much you twist equals to how much torque you apply to the material. L is the geometrical information. G is the material property. J is the cross-section area, representing some parameter about the cross-section area. So similar to normal stress analysis. Earlier we have which equation? I didn't write it down here. Anyway, so from here, just I want to comment on how material deform is related to the force you apply, the geometry of the design, the material property, and also the direction of your force. Okay? So please remember those. Now back, let's put everything together. Let's try to bend and twist a cylindrical geometry, like a shaft or a rod, any way you want to call it. So same equation as what we mentioned earlier. Sigma equals to n radius over I, tau equals to t times radius over j. Okay, I try to use the same symbol for both equations. And since this time we are working on cylindrical object, so we need to check the textbook or internet about how to compute the area moment of inertia. If we work with Ix and Iy, they're the same because it's axial symmetrical. So that's why these two are the same. If you are curious how to get those, you can check how we make the integral, and you can prove it by yourself. Try it once and see if you can get the same value. So as I mentioned, J equals to Iz equals to the sum of both. So we have 2 over here. Now we want to put them into our equation. At the end, we have these two guys. Those who are so commonly used in this course, you can almost just deeply memorize them in your mind. Okay? 32m over pi dq and 16t over pi dq. Because later on, we won't spend time on deriving those anymore. We directly use it. Okay? So these two, please make sure, try to memorize it. Although in my exam, I usually like to give you a list of equations, so you can still get some hints from the equations I give you. However, usually I don't give the equations in a proper order. So I like to scramble them. So you need to figure out what equation is for what question. Okay? You need to figure out by yourself. And I don't guarantee to give away all the equations. Maybe I give you this guy, maybe I give you this guy, I want you to plug in by yourself. Right? So you cannot 100% rely on the equations I give you in the exam. You don't know what equations will be provided. it would be better for you if you have some memorizing something. Okay. So there's there's a proof. I did it. Okay. I don't want to spend time on this. So this is available on internet, on our webpage. So you can try it by yourself. Okay. Oh, this is the proof for bending. I did it. Okay, and that's for twisting. Good for your reference. Here's the comparison I want to show you. So, for normal stress and shearing stress, they have some similarities in equations. I put them together so that you can easily find a relation. So the first equation basically describing elasticity. How stress and strain are linearly related with each other. So stress equals to Young's modulus times your strain. Shearing stress equals to shear modulus times your shear strain. Okay, very similar equation, but completely different phenomena. One is normal to a surface, the other one is lying on the surface. So when we talk about normal force, you have the deformation along length direction. So this is how much, like if you pull this, how much increment you have. This is the sigma. Now the delta. This is the delta. How much you pull. So the deformation along the linear direction equals to how much force you apply over material property, Young's modulus, and with some geometrical information, length and the area. Similarly, if you twist, the twisting angle equals to how much torque you have over the shear modulus, also some geometrical information. However, here we have J, here we don't have I, okay? They are not exactly the same, but they look very similar. Okay, but for these two, they are very similar. The stress, normal stress, shearing stress, moment times the radius, or the distance away from the normal, the neutral axis, over area moment of inertia. Tau shearing stress equals to torque times radius over the polar area moment of inertia. And we are dealing with cylindrical object, directly applying the I and J to the equation. At the end, we have these two commonly used equations in the course. Try to memorize them. Now, we are moving really fast, directly moving on to a shaft being bended and twisted at the same time. Now, basically we're doing this, twisting and bending at the same time. When this is happening, as you can see, if you try to observe somewhere surrounding the entire shaft, they have different the stress conditions. Okay, so let's take a look at the top one. Okay, so over here, it's having a maximum distance away from the neutral plane of the bending, regarding bending. Okay, so the horizontal plane right here is the neutral plane, and we are bending the shaft like this. So at the very top, we should have the largest normal stress due to bending. So over here, when we try to draw a big picture like this, you need to clearly specify how you observe this small point. Actually, it's a point. But we usually like to draw this on like a square. because we want to emphasize how the forces are applied to this small piece of surface following certain direction, along certain direction. So when we draw a square like this, we tend to draw in parallel with the coordinate system. So here is our x, and going this way is our z. So we are observing from top down, from top to down, to here. So this is how we observe. That's why z is going downward. Okay? Now, due to bending, we know there is a pulling force going right here, and there's a pulling force going left. And these two forces can generate the stress at this point. And that's why we have this pulling stress, normal stress, going left and right. And the amount can be actually computed 32 times the moment that you generated over pi d cubed. Okay? That was mentioned earlier. So if we try to observe what's the opposite side of this point at the very bottom, in that case, because of bending, the bottom side has compression. So in that case, this is going into the material. It's a compression stress going in. Okay? So please make sure you understand why that's going outward. And if we observe at the very bottom, it's actually going inward. How about this point? Over here, because we are on the neutral plane, so there's no stress. There's no normal stress. That's why on this horizontal plane, when we observe on the side, there's no normal stress. Okay? So please make sure you can visualize this. Now, how about twisting? Twisting is going everywhere, surrounding the entire surface from the edge of this rod, of this shaft. So it's going, you have like a torque going this way. And on the other side, you have another torque going this way. So this particular small area is being twisted. On its left-hand side is going up, and on its right-hand side is going down, like this. And you know, shearing force always comes in a pair. So when this goes up, and this goes down, and then this goes left, this goes right. Okay. And it's exactly the same for the entire everywhere surrounding this shaft. That's why the shearing stress is exactly the same. Okay. So make sure you know how to get this. So that's the end of my current PowerPoint. Any questions? This should be something you have learned already. Okay, great. Now I'm moving on to the other PowerPoint. Now, it's time to study a beam, okay? The beam could be having a cylindrical cross-section, or it could be having a rectangular cross-section. It doesn't matter, okay? When we are talking about a beam, it's like a long item, and then we call it like a beam. Now, here's the situation. For a shaft, it doesn't always carries uniform or simple loads like what we showed in the previous PowerPoint. it could be carrying so many different components in a machine. So it's really important for us to compute the stress distribution everywhere inside the entire beam. That's why we need to do this stress analysis in a beam problem. Okay, so what's happening is this beam could be having a distributed load, Wx, from the top. Okay? If you observe somewhere at x and make a tiny cut with the width of dx, that particular piece is shown right here. And Wx could be changing everywhere. However, when we are focusing on a small cut right here at position x, the amount of W, let's say, equals to W. And it's exactly the same within this small area because dx is so small. So W is the same value. Okay? So this is the zoom in version of this guy. And we could be having shearing force and bending moment from both sides. We don't even know the direction. It could be bending down or bending up or shearing this way or shearing this way. We don't know. So it's really important for you to make a decision how you make a drawing. So when you make a drawing like this, you decide, okay, I assume on the left, bending this way is my positive moment from the left. Okay, and shearing up from the left is my positive shearing force. This is the way you define it. Okay? At the end, when you do calculation, you find out, and if it's negative, that means it's bending the other way. And if you have a negative V, that means it's shearing the other way. Okay? So at the beginning, you want to make sure you properly define the coordinate system. Now, as a system, because of the balance of force and balance of moment, if you have bending this way, then on the opposite side you have a opposite bending moment along the other direction. Similarly, you have a different shearing force going down. However, why do I say plus dV and plus dm over here? Because at exactly same point, V equals to V. For example, if we are standing right here, we have exactly same shearing force up and shearing force down. So it's shearing the surface. At exact same point, we have the same moment bending this way, and the other side is fighting against the moment. So exact same amount of moment bending the other way. So they have balance. However, we make a movement toward right a little bit. We move a little bit. So with that tiny movement, the amount of shearing force and bending moment could be changing by a little. So this is assuming shearing force increase a little bit. This is assuming moment increase a little bit. So can dm and dv be negative? Yes. So this is just to assume, symbol-wise, we have some change. So when I move toward right by dx, shearing force and bending moment increase by dv and dm. They could be positive, they could be zero, they could be negative. Just to define some symbol over there to show shear and moment could be changing. Once you have that, then the rest are just derivations. First, we use the balance of force and moment on this pink rectangle area to derive the following equation. First one is the balance of force. So whatever goes up is on the left-hand side of the equation. Because W is a distributed force, so the unit of the force is actually force unit over length in this particular case. Okay? So you can say it's a Newton over meter. So W in this case is having the unit of force over length. So if you want to compute the entire, the total force generated by that distributed load, you have to multiply how wide it is. So W dx is the total force contributed by that distributed load, W. Adding the upward V equals to the downward V plus dV. And as you can see, these two V cross out. At the end, you have W equals to dV over dx. So what's interesting is that if there exists some distributed load on the top, that will generate some increment of the shearing force. That's the key idea. If there is distributed load applied to the system, by moving from the left to the right with the length of dx, the shearing force will be increasing the amount of dV. Okay? So that equation tells us this story. Let's talk about the balance of moment. If we make a cut into half, supposedly the center is right here. So V plus dV times half of the width, that's the moment generated by this guy going clockwise. V times also dx over 2, that's this guy, and making a moment also going clockwise. The other guy generate a clockwise moment is the n right here. So only thing that's doing counterclockwise, that's n plus dn right here. How about W? If you have a center right here, the left portion of the force going clockwise, the right portion goes counterclockwise, they balance out because it's a symmetric geometry. So you don't even need to put them in the equation. Now you can cross out some of the terms. Over here, this guy disappeared. Because dx is very small, when you have dv times dx comparing to dx, this is super small. So this guy, this disappeared. This is almost zero. Okay? If you can do that, then when you collect everything at the end, you have V equals to dn over dx. So if you have shearing force applied to the geometry, and then you walk from the left to right with a distance of dx, your moment increased by dn. That's the idea. So if shear exists, then your moment increases. Okay, those two are very important equations. Now, when we have those two, we can then take integral of those. Before we do that, sorry, we need to talk about this guy, then we can take integral. This guy is a longer derivation. We want to study deflection. In Chinese, it's called 挠度. And what is that? It's the amount of deformation along the y direction after you apply the distributed load. So if you have a distributed load on top of the beam, your beam could be bended in a very weird way. The amount of deformation along y direction everywhere is called deflection. Okay? Now, we derive this using this figure. So, this is this guy being deformed. Okay, this is after deformation. We exaggerate how much this geometry is being bended and having this new shape, looking like a piece of the pie, right? So, what do we look at first? Maybe we need to know what each symbol represents. So, because this is being bended, and only at the neutral level, there's no length change. So originally, this is dx. Even after bending, we assume at the neutral plane, there's no length change. That's why this arc is remaining dx. However, this becomes shorter, this becomes longer. Okay? And this is the curvature. Curvature rho, and due to the curvature of rho, and if you make a tiny tangent, make a horizontal drawing like this right here, this point actually move up a little bit. So we call this is how much your neutral point moved along the y direction. So this is actually the increment of deflection. So if you keep on counting how much your neutral plane move up or down, then you know how much deflection you have. Okay, and how come this is dx and this is how come this is d theta and this is theta? Okay, because this is being exaggerated. If you truly try to make a drawing, this is a bended beam, and you are only making a tiny cut right here, so tiny. So you cannot even visualize dy. And let's say this is the center of your rotation. Okay, so this is your rho, basically the radius of this curvature. Okay, and of course it's on the neutral axis. So this is your rho. Now, if you only move a little bit from left to right by dx, this angle is so tiny. It's like a very tiny move. The angle only moves by d theta. So which one is theta? Theta is like, if you say here is theta equals to 0, then here this is theta. If you define your rotation in this way, if you say somewhere is theta equals to 0, then from that base going up to this position, that's the total theta you have. Okay? And by moving a little bit from left to right, that theta only increases a little bit. Okay? So that's ideal. But how come this guy is beta as well? Because that's, you actually, if you truly bend this beam into a circular shape, okay? Give me a little, some time. If you truly bend this geometry in this shape, and this is beta equals to 0, and here is theta, and then you are just focusing on this small portion. In that case, this guy is truly beta, okay? So we will continue after we take a break, okay? I will continue and then go through this, and then we can talk about the equations. So take a break. For attendance, you can use this QR code. If you want, you can do it now. So another thing to announce. A minute. Sorry. Another thing to announce, which is about our course scheduling. In one of the week, we mentioned that we want to have lectures of finite element method or finite element analysis. It's a numerical software that simulates how structure deforms. So you don't truly need to make something and then do some tests in order to figure out the stress distribution of the object. You can actually do it in computers. So there's one lecture. I will invite a company who sells the software, and I will invite them here to give you short lectures about how to use the software. So on that particular week, unfortunately, this course was about pure lecturing, not mainly designed for computer labs. So we couldn't find a computer lab for this person's presentation. So on that particular day, we still meet right here. So he will be giving away lectures about some software operation and the fundamental of finite element by presentations, by PowerPoints. And we will video record his presentation. So later on, if you want to review, you can always check on the video. However, for you guys, after the course, if you truly want to use it for your project, there are two choices. One, you can come to our lab. We do have computers with the software. Two, you can go to the computer lab in our department on the second floor. Each computer in the computer lab on second floor of engineering building, first engineering building, has the software that we're introducing. So originally, I want this to be done in a computer lab. We cannot. And originally, we want to do an exercise in the computer lab. We also cannot do it. So on November 8th, this exercise canceled. We cancel this finite element exercise. You don't need to come here. You don't need to go anywhere. We just don't have a lecture for this exercise. So you need to use your own time, go somewhere, find the right software to practice this. Okay? So please don't come here. No one will be here. Okay, on the 8th of November. Any questions? So it's on the syllabus. It's updated here. If you later on check it, figure out there's no class. Don't be surprised. Okay.
Sir?
Yeah, go ahead.
So on the night, will there be any exercise related to that?
So we won't prepare exercise for you. You basically find self-learning. You can come to our lab, use your own time, go to the computer lab, it's mostly open if there's no lecture. You can just sit in and then use it. Or find a copy in your computer by some, I don't know how to, I don't want to teach you how to do it. By some way, okay? So, back to our lecture. Now we know what's everything about that banded geometry. First, we will take a look at this particular area. So originally, the bottom half, bottom edge, has a length of dx. After bending, it was lengthened by this much. So how do we compute this? We can use the radius times the angle right here. So this angle is the same as d theta. The radius right here is c. That's why this increment is almost the same as the arc length right here. So it's a c times the d theta, same angle here and here, okay, due to symmetry. So this increment c d theta is actually the increment of the bottom edge after bending. So if you have the increment over its original length, that's the definition of strain. That's how we have this equation. And strain equals to stress over Young's modulus. And also, stress equals to mc over I. So overall, from the first one and the last one, we can cross out c. So d theta over dx equals to m over ei. That's a very important equation right there. What else do we want to do? We want to, okay, move on to the next equation. Yeah, because we want to rewrite d theta over dx even more. So we can come up with deflection, because we want to know deflection, not theta. We want to know deflection. So in the second equation right here, it's using the relationship of somewhere right here. This is rho, this is dx, right? Very tiny, small piece of pie right here. Very thin pie right here. But the radius is rho, the theta increment is dx, and the arc length is actually dx. So you can have rho times d theta equals to the arc length right here, dx. So very thin pie right here. Okay? Now you can get d theta over dx equals to 1 over rho. And also, another important one is a relationship right here. There's a tiny rectangle right here. So because the angle is also very small, then you can get theta is almost the same as dy over dx. It's like or you can use you can say the radius times theta equals to arc length. If you can treat it like that. So theta right here is almost the same as dy over dx. Okay? Now, or you can say it's like a sine theta, right? Sine is this guy, and this guy over this, right? So dy over dx. So with everything that we had, d theta over dx equals to basically taking derivative taking derivative of theta. Basically, we are taking derivative of this equation. So at the end, we have second order derivative of y with respect to x, and this equals to 1 over rho, and also equals to over here, the result right here, n over I in EI. Okay? So the important equation that we need actually is y double prime equals to n over EI. If we have that, we can take the integral twice. So y would be equals to you just need to take the integral twice. Then you can get y, right? That's how you can compute deflection. So the key of this slide is to get this equation. If you know how much moment you have at any point, if you take the integral twice, you get how much deflection you have at that particular point. So later on, we will have some exercise. We will be doing, we need to do this, okay? So to sum up, at the end, n over EI equals to y double prime, okay? And since we have these two equations right here, you can take one more derivative of m, you will have shear. You can take one more derivative, then you can have the distributive load. This is how they are related to each other, okay, by several times of derivatives. Okay. Do we? I think we covered this already. This is about Mohr circle. Do we focus on the problem? Maybe we talk about the problem first. Let's work on the problem. Let me see if I have a problem. Yes. I think it's one of the previous exam problems. Okay, so now we can already do this. We can already do a problem like this. So what's going on? There's a shaft, and it's carrying two pulleys, and there are belts pulling from both sides, and pulleys on this particular pulley is pulling up, and these two blue ones are bearings. Okay, so this shaft could be rotating or not. Okay, it could be staying at the current situation, or it could be rotating. So what's happening is we name these positions A, B, C, D, E, and F. And we specify the distributed loads. W1 equals to 5 Newton over millimeter. W2 is 7. W3 goes up is 15. W4 is 13, goes up. And then the reaction forces applied surrounding the bearings are called R. So RA represents the reaction force at position A. RA, the second index Y or Z represents its direction. RAY goes up. RAZ goes toward you guys. RFY goes up. RFZ goes toward you guys. Now the diameter of the shaft here is 35 everywhere. The diameter of the pulley is 75 for both. Now we need to do a lot of calculations. We need to first compute the reaction forces, and then we need to compute the shear and moment. And then we need to figure out which position has the worst loading condition. So we can compute up to here, A, B, and C. D and E, we can do it tomorrow. Okay, so let's work on it. Basically, we will analyze this problem in two different planes. I think the first equation, balance of moment, I am focusing on the XY plane. I don't care about anything on the Z direction. And I am choosing, let's see, which one has a, let's see, 10 plus 80, 50, 90, 25. Okay, I'm choosing point A as a supporting point. So this RAY doesn't need to be included in this equation. I'm choosing it as a support, okay, as a center. So only forces that is generating a moment against this point A is the forces right here and then RFY going up. So I here need to sum W3 and W4 together, multiplying its width, 50, and multiplying the distance. And this RAY is not, the point A is actually right at the center, right here, not at the edge. So point A is having a distance of 10 from the origin. So going this is the true center. And then I'm summing 10, 80, 50, 90, and here summing 25. See, 10, 80, 50, 90, and 25. So that's the true distance of this force that is generating a counterclockwise moment about this point A. And then Fy is also going counterclockwise. So 10 right here because only half. 80, 50, 90, 50, 80, and then 10. Only half right here. So RFY times the entire distance from this arrow to this arrow. So that's your first equation. Similarly, what did I do in the second equation? I think I chose 10. I don't know why I chose this point. I chose this point. Secondly, in the second equation, I chose this F point as the center. So W3 and W4 is generating a clockwise moment. The distance is 10 plus 80 plus 25. 10, 80, 25. And then RAY is also generating a clockwise moment. So the distance would be the same from here to here. So with those two equations, do some math, you can get IFY and RAY. Okay? And at the end, you get negative values, that's fine. That means they're actually going down. Similarly, I'm working on the XZ plane, the horizontal one. Very similar procedure. I don't want to spend too much time. So check it on your own. Now, that's everything I need for the answer A. For the first exam, I plan to give you a very similar problem. Okay, so the first question I will ask you will be compute the reaction forces. My worry is, do we have enough time to compute everything? So I recommend you to do a homework I mentioned we are going to have a homework. I recommend you to get familiar with those equations. We should give you a homework tomorrow. So once I finish this entire this example, I will give you a homework. Very similar to this problem. And next Wednesday, we will have an exam. Most likely, I will give you a very similar problem like this. Maybe just some value change or geometry change, but similar type of problem. Only worry is, can you finish within 1 hour? Okay? Most likely, only one problem. So please make sure you understand what's going on. It should be quite simple. Should be quite simple for many of you, but I still worry some of you are not familiar with this. So please get familiar with this. Now, this part. This part is how you can get the shear everywhere inside the shaft and moment everywhere inside the shaft. So let me ask you a question. Who doesn't know how to do it? Okay, who knows how to do it? So you either know or don't know. Okay. How can I get an answer from students? So should I bring money? Anyway, it's very important to be able to get this. But there are many ways to get it. So I think this is probably important part in mechanics of materials. I'm just reviewing it. In the previous presentation, you can actually use everything that I introduced in this particular slide to get how much shear you have, how much moment you have. But I don't usually use this way. It's too slow. So I'm going to show you how I get I'm going to use a faster way, okay? And I guess many of you already know how to get this really fast. But if you are not familiar with it, please bear with me and see if you can learn something today. So if you have a shaft, and you already know the reaction forces. So usually we have, this is shear force, right? Shear force. And I'm talking about the x coordinate, and I think this is the y coordinate. Is it? Y direction, yes. So I'm talking about, yes, the x, y direction. And in the previous slide, we already know. Let me directly draw where the shaft is. This is the shaft. We already know somewhere right here, there is a reaction force going downward. Okay? So usually I will take a walk. I will take a walk from x equals to 0, and then I will walk toward right. Okay? And whenever you meet somewhere that has a reaction force, either up and down, then your shearing force will be increased by that amount. Since we have a reaction force going downward by certain value, then my shearing force strictly goes down to a certain level with the amount of negative 435. So earlier in the previous slide, we said RAY is negative 435. So over here, it's pulling down. It's pulling down 435. So for the shear force,
diagram, when you walk toward right, when you meet a reaction force, individual force, then it's pulled down up to a certain level. Then you keep on walking, so your shear force remains the same until you see distributed loads. So over here at, this is position A, this is position B, position E. So up to here, up to position D, that is where you see the distributed loads. For the distributed loads, you will be increasing whenever you walk toward right. And there's a slope. The slope. Slope will be equals to how much distributed load you have. So over here, which is 28. Why? Because W3 plus W4, 15 and 13, that's sum them up is 28. Okay? So why is that? If you go back to your the slide that we introduced right here, whenever you have W is when you take one more derivative, you have W. Where do we have this? Oh, this is right here. So if there exists the distributed load, when you move by a little, then your shear force increase by a little. And dV over dx, that's exactly the slope of the shear force. So this is telling you the slope equals to how much distributed load you have. And since in that particular problem, we have constant distributed load, right here, from D to E, the distributed load remains the same level. So we have a constant slope. So if we have varying distributed load here, then this increment of your shear force will be nonlinear. That will be more complex. In my exam, I won't do that because you don't have time for that. Okay. But for you to know why we have this. Now when we are reaching to point E, we'll keep on walking toward right. Since from E toward right, there's no shear force, so this remains the same until we reach the last point, and then we go down. The last point is called F, right here. And this amount is negative 965. So usually, when you make a wall from the very left to the very right, it ends up with 0. If it doesn't end up with 0, something was wrong. Somewhere you computed wrong. Okay? That's the usual case. Now, if you have this already, you can directly, hold on, let me remind you, the slope, W equals to dV over dx. Okay? And if you already have shear force, you can quickly get the bending moment by the following equation. Because we know if we if you take integral of V, then you have moment. So V equals to, so you can say N equals to integral of V dx. And if you take an integral of V, okay? That's what we are going to do. So over here, this value right here is negative 435. This value here is positive 965. Okay? And in fact, you can formulate equations right here. This is Vx equals to negative 435. Here is Vx equals to 965. How about this guy? This is actually Vx, slope is 28x, plus a constant. I can call it C1. Okay? I did the same thing here, C1. So you want to know the equation first. Then when you take the integral, it's easier. So the way I computed C1 was to plug in a number. So I plug in the position 240. That was the position. This is 240. So just plug it in. So at the end, V240 equals to this particular value. So it's negative 435. So that's how you can get C1. You can get this guy. Okay? So you will have the exact equation of the shear force in this portion. Then when you take integrals, you can easily get those three. From those three above, you can easily get the integral equations right here. However, you do have constant values, C2, C3, and C4 to be determined. Okay, so you know you will end up with a shape like this. You just don't know where exactly, because there's a constant value. So you need to have some boundary conditions in order to get the constant. So how do we get the boundary condition? You need to have some common sense. So over here, when you take a walk from the left or right. When you walk to up here, you suddenly have a shearing force, and that's where you start to have some bending. So before that, there's no bending. Up to here, you started to have some bending. So that's the exact location where you have zero bending moment. And then when you start to walk toward right, the bending moment start to increase its value. Either it's positive or negative. So you can use position 10 right here. At that particular place, the moment should be zero. So you plug into this value, this equation, you get the constant value right there. Similarly, you can compute how much moment you have right here, because you already know the constant of this guy. So you can plug in 240, the position, then you can know how much moment you have at this particular point. Then this is how I get it. I got it. Next, we have a second order quotient. It's like a curve equation right here. Because earlier we have a linear equation, after integral we have a second order equation, the polynomial. And you can use the information of this point, plug it in, position 240, moment, this guy, to get C3. Okay, to get C3. And then I computed this particular point again using the position of 290. Plug it in, then I know this value should be this value. Okay? You can use this particular point to get C4, or you can use this point to get C4, either way. This point or this. So over here, because there's no more force on the right, so the moment should be zero. So you can plug in 380, and your moment should be zero. So that's how I got C4.
So in the exam, you should be able to compute moments. So in this particular case, where has, at which position we have the most largest moment? Can someone, bending moment? At which position? Here? Where? The largest? Here, right? Like at the tip. Somewhere, right here. It's not exactly 240, not exactly 290, it's somewhere at the bottom right here. Okay? That's the position that has the largest bending moment. And remember, our stress equals to moment times C over I, right? So at that particular position, this value is the largest, C is the same, I is the same everywhere, C is the same everywhere. So at that position, N is the largest. So over that particular position, we have the maximum stress. So if I really want to break this shaft, it will crack or it will permanently damage at that particular position. Okay? So, same analysis along the Z direction. This is the same analysis. So I'm not going to go through again. This is how you can compute the maximum moment. So in both cases, at the bottom edge of this second order equation, remember when we were probably in high school, when we try to find the extreme value, we usually say, okay, y prime equals to 0 gives you the extreme value, right? So this is what I did. I take first order derivative and make it equals to 0. And that gives me the exact position where we have the minimum. Same here, take first order derivative and make it equals to 0. I get where is the position with minimum moment. Actually, is the most negative moment. And that actually is the largest moment. Okay? But negative represent compression. Okay. Now, what else can we do? Because this shaft is carrying moment along both y and z direction, so we need to observe moment along both directions. So if you want to do it right, you should do this. I will guarantee you in the exam, I won't give you two direction, no problem. Only one direction, no time for this. But in the practice, I want you to learn how to do it. So at this particular point, we have moment along y and moment along x. At this particular point, also moment along y and x. You can plug into those equations to get the exact moment in y and z. So if you take a look from the side, it's like this. If this is the cylinder, and if this is your x, this is your y, and this is your z. In this particular case, we are trying to visualize at two different positions. And we do have moment going this way. This is 103,462. And then we have another moment along the negative z, so it's going this way. That was 23210. So we have moment along two directions. So we want to have a sum
or combination of two vectors. So we end up with a new vector. We end up with a new vector right here. That's the total moment. So the total, this is the total moment. And it equals to 2, 3, 2, 10 squared plus 1, 0, 3, 4, 6, 2 squared. Sum them up and then take a square root. Okay? Did I do it? Oh, I haven't done it yet. There's the next slide. Yes. So if you want to truly compute the total moment, this is how. Okay, so I did the same thing for this particular point and this particular point. So overall, the largest total moment happened at the position of 2, 5, 6. That's the worst position. And what was the direction of the moment? It's going this way. It's actually going this way. So what does that mean? That means you have it's not banded along y, it's not banded along z, it's banded along a if you visualize from the side, this is z, this is y. It's being banded along this way. It's banded toward a angular direction. Okay, so in fact, that's the situation. So I want you to understand this is what truly happened. Okay? So you can do this. To study the stress, so in fact, at that worst loading position, if you want to compute the stress, you need to use the total moment. So I'm actually using the total moment. This is a total, I think this is a total moment, yes. 32 times total moment over pi d cubed. This is a true stress. But so the stress is along some angular direction, okay? So this is how you compute stress. But for the torque is the same. Torque everywhere is the same. So how do you compute torque? If you realize W1 and W2, W2 is 2 larger than W1. So 7 minus 5 is 2. W3 is 2 larger than W4. So if you do W2 minus W1, that's 2 Newton over millimeter. If you do W3 minus W4, that's 2 Newton over millimeter. So that's how the system is being twisted. This and this, it's like this, twisting this way. Okay? Same amount of torque. So I use the torque. You can compute the torque right there, the same amount, and use the same equation. So at the end, you have actually at the worst case position, you have 25 megapar and 0.4 megapascal in shear stress. Then you can actually draw the stress diagram like this. You have normal stress, and then you have shear. The amount was computed. And for the Mohr circle, I will cover tomorrow. Okay? Actually, we can compute deflection if you want, but it's very difficult to compute deflection in this case because it's going toward a weird direction. If you want to compute deflection, then you need to compute the deflection along y and along z, and then use a square root to sum them up. Okay? So I think I'm almost out of time. Tomorrow I cover the Mohr circle. Then we can talk about the principal stress, maximum shear stress. They are very important to failure model. In the future, we only talk about principal stresses, maximum shear stresses. Most of the design models were based on principal stresses and maximum shear stresses. So from now, you probably can tell I will be going pretty fast. You may need to do some self-study after the course. I hope you have learned this already. Later on, when I move on to the true model that is only introduced in this course, you need to have full understanding of what I introduced today. Otherwise, when I move on to the true model, you may get lost. Okay? So we still have a week for reviewing the mechanics of materials. If you are a little bit lost today, then you need to spend some time after the course. Today the TA has something for you to sign because we are running the Ministry of Education project. They require everyone to approve being participating in the program. So please sign for us. That doesn't count to any of your score. Don't worry. Just please just sign. Okay. So today on the course webpage, today I already covered.
Keep yourself and one will return back to you. Okay?
Let me see which one.
And everyone will get 2 documents. And one will keep in yourself and one will return to me. Okay? You need to sign 2 documents.
Okay, so on the webpage, the PowerPoint I used for today was the PowerPoint in the same semester 111-1, as the same PPT in 111-1. I specify right here. Today I use this particular one and this particular one. Okay, I kind of jump a little bit, so I will update my webpage. You can go to the 111-1 to get the PowerPoint. Okay. as mentioned right here. Okay, so if you haven't done this for attendance, please do so. Once you finish signing the form and scanning the QR code, you are done for today. Thank you. Oh, who was not placed in the group? If you are not in a group, find TA. Okay.
Did everyone return back a document? Okay.
因为那个日程计划是去年写的，因为计划已经交出去了，所以我是前年用那个交出去那个时间的日期。我不知道你们会有疑问。留言没有，那就要。谢谢。会加选择，然后你有看我帮我打几个学号，今天都点不到，你要不要后面帮你画那个色标？先帮我这里点，前面这边，然后等一下再来看左边，地方啊，对地方，这边左边我觉得会有。